In this lesson, we are going to talk about what is a power. So if we have a square here, how can we use the side length of a square to calculate its area? Well, you've learned in previous classes that the area of a square is side times side, or side squared, or length times width. So one thing that we know about the property of a square is that all sides are the same length, and these little tick marks indicate that they are all the same length and they all have 1 unit of measurement. So if we wanted to find the area, we would go 1 times 1, that's length times width, which is 1, or we could go 1 squared, because area equals side squared when you are dealing with a square. A Rubik's Cube. What do we know about a Rubik's Cube? Hopefully you recognize that all side lengths are 3 units. And so that's why it is called a cube. All sides have the same measure. So 3 units no matter which way we go. So how can we use the edge length of a cube to calculate its volume? Well, again, from previous math classes that you would have taken, you can know that the volume of a cube, you can either go length times width times height, or it's side cubed, because all sides are the same. In this case, it's 3 times 3 times 3, which is the same as 3 cubed. How could we check our answer? 3 times 3 times 3 gives us 27. How could we check that this was correct? Well, you could build a cube, or you could take a Rubik's Cube and take it all apart, and you would see that there are 27 pieces to it. So let's put this together and figure out what it is we're trying to talk about. When an integer other than 0 has special properties, can be written as a product of equal factors, we can write the integer as a power. So if you've got 3 times 3 times 3, those are all equal factors. They're all 3. So we can write that as a power, and that's what it's showing in this red circle. This is a base of 5. 5 is the big number, so we call it the base. The exponent is the little number up to the right of the base, and we call that the exponent. Altogether, we call it a power, and in this case it's a power of 5 because the base is 5. So we say 5 is the base, 3 is the exponent, 5 to the exponent 3 is the power, 5 to the exponent 3 is a power of 5 because 5 was the base. We can also say that it's 5 to the third or 5 cubed. Anything that has an exponent of 3 means it had occurred 3 times, so in this case it would be like 5 times 5 times 5. And anytime you have 3 identical measures, you can make a cube from it. So an exponent of 3 we also call a cube. So a power with an integer base and an exponent of 2 is called a square number. And that's because to find your area of a square, it's side squared, s to the exponent 2. So let's look at the number 25. We can write it different ways. We can write it in what's called standard form, which is just 25. Or we can write it in what we call repeated multiplication. So that's when you take the same number and you multiply it over and over until you get that standard form. 5 times 5 is 25. And because the 5 repeats, we can write it as a power. It repeated 2 times, so we say it's 5 to the exponent 2. So when the base is a positive integer, we can illustrate a square number. So if it's an integer or an exponent of 2, we can actually draw a square. And in this case, it's a square with side lengths of 5. So we can draw a square, and you see this has side length 5, 5, 5, 5. And if you were to count all of the little units inside, you will get 25, which is why 5 times 5 is 25. So any square number, any exponent of 2, you could demonstrate with a square, assuming the base was positive. A power with an integer base and an exponent of 3 is a cube number, and I briefly discussed that when we looked at the Rubik's Cube. So here are 3 ways we could write the number 125. Standard form is 125. That is the number we are talking about. Repeated multiplication. 5 times 5 times 5 is 125. And it's repeated multiplication because the numbers are the same. So we are repeating the number while multiplying them together. As a power, we say this is 5 cubed, or 5 to the exponent 3, or 5 to the third. When the base is a positive integer, we can also illustrate a cube number. And all we would do, we know that in this case, each side length has to be 5. So there we go. I can split it all into 5s. And then we got to split this one into 5s as well. And then we have to break it into rows of 5, because every single side length has to be 5. So we can see 1, 2, 3, 4, 5. That side length is 5. 1, 2, 3, 4, 5. Side length is 5. 1, 2, 3, 4, 5. Side length is 5. You could go all the way around this cube, and that is what you would see. And if you were to build that, you would have 125 little cubes put together to make up that big cube that has 5 by 5 by 5 dimensions. 4 to the exponent 5. What does that mean? Well, in repeated multiplication, it means it's 4 times 4 times 4 times 4 times 4. It is repeated 5 times. Whatever your exponent is tells you how many times we repeat the base. When we multiply that all out together, we get 1024. Could you represent this concretely? So that means, could we build it? Not very easily. We don't have the capability, or at least I don't have the capability, to draw a 5-dimensional figure. Some computer programs might be able to do that. But it is very hard. It's not like a cube where we can take a bunch of linking cubes and build it, or a square when we can take a bunch of squares and make a bigger one. It's hard to make a 5-dimensional object. Let's write as a power. So what we have right now is repeated multiplication. We want to write that as a power. Now remember, the number that's being repeated, that's the base. So we know that this is going to be 3 to some exponent. To find out what the exponent is, it's how many times this is repeated. And it's repeated 6 times. So it's 3 to the exponent 6. When we have the number 7, 7 is our base. How many times is that 7 repeated? Only once. So it's 7 to the exponent 1. Any integer on its own has an exponent of 1. We just typically do not write it there. So this time we want to write as repeated multiplication and then in standard form. So 3 to the exponent 5. The base is what gets repeated. The exponent tells us how many times we repeat it. So our base was 3, the exponent was 5, so it gets repeated 5 times. And then in standard form, it's 243. 7 to the exponent 4. 7 is our base, so that is what gets repeated. The exponent tells us how many times we repeat it. So 7 times 7 times 7 times 7 is 2,401. All right, so far we've dealt with just positive bases. The negative base becomes a little bit tricky. We have to determine if the negative is part of the base or if it is a separate part that was just being multiplied to the power. So we want to identify the base of each power, then evaluate. So when we look at this first example, negative 3 to the exponent 4, what we have to do is we have to determine whether that negative is a part of the base. And we can look at if there's brackets. And then where do the brackets separate things? In this case, the brackets separate the base from the exponent. Notice the bracket is between those two. The negative is inside the brackets, so the negative is part of the base. That exponent applies to everything inside the brackets because the brackets separated the exponent from the number part. So if our base is negative 3, repeated multiplication is the base multiplied however many times there was an exponent. So negative 3 gets multiplied 4 times. And a negative times a negative times a negative times a negative is a positive number. So our answer is just 81. Now if you look at B, negative 3 to the exponent 4, you may think it's the same thing. However, this time there is no brackets. When there's no brackets, this is actually the same as saying negative 1 times 3 to the exponent 4. That negative is not attached to the power of 3. So what we have here, the base is only positive 3. So what we're multiplying here is we're multiplying negative 1 times 3 times 3 times 3 times 3. So our answer is negative 81. So when there are no brackets, that negative is on its own. It's just a negative 1 times the power. Let's look at C. We have a couple of negatives here. We have some brackets, so we have to determine what is part of the base and what is separate. The bracket separates the exponent from the base. Everything in that bracket is part of the base because the exponent is outside of it. So the base is negative 3. But the negative that's out in front here is extra. This is like saying negative 1 times negative 3 to the exponent 4. So when we multiply this, we've got negative 1 times negative 3 4 times. So what we have here is we actually have 5 negatives, which means our answer is going to be negatives. An odd amount of negatives will give you a negative answer. So it will be negative 81. And in the last one, again we have brackets. But do you notice a difference about where the brackets are placed? The bracket is not separating the exponent from the base. Notice the bracket is outside of everything. Unlike back in this example here, where the bracket was between the base and the exponent. In D, the brackets are useless. This is the same as saying negative 3 to the exponent 4. Those brackets were outside of everything, so they do not play a part in this one. So now we are back to the same as B. This is the same as negative 1 times 3 to the exponent 4, which is negative 1 times 3 4 times. So there's only one negative, so our answer is negative. So it's very important to look at where your brackets are placed when you're dealing with negative numbers. If the negative is inside a bracket and the exponent is outside of the bracket, the negative becomes part of the base. And that's what happened in A and C. But if there is no brackets, or if the bracket does not separate the exponent from anything, then the negative is not a part of the base. It's like saying negative 1 times that power.